Right, we have a chapter 8 question for heat transfer. So we have gases going through a tube, and we have hot gases enter at 115 kPa, 250 degrees C, and a mean velocity of 5 meters per second. They leave at some other temperature, and we're given H. We're given the surface temperature, and we want to figure out the tube length and the rate of evaporation of water. We're given some of these other numbers over here that may be beneficial to use, and I'm going to throw one more on there, this gas constant R. Because these are gases, we can actually use the ideal gas law to solve for density. So that's what we're going to do first. So density is equal to P over RT, or not, yeah, density is P over RT. So now what we're going to do is we have 115 kPa, so what I'm going to do is I'm going to divide this by 1,000 because this is in kilojoules. So 115 pascals times 0.287, and we want this to be in Kelvin. So what we care about is this 250, so 250 plus 273. That way, the units for density end up working out. So if you wanted to keep this as 15 times 10 to the 3, you'd have to multiply this by 10 to the 3 to get it in joules instead. So this gives the density at the entry of these gases. That's 0.766 kilograms per meter cubed. But now we have the density of the gases that enter the tube. Then I'm going to grab the mass flow rate now that we have the density. So that is rho AV, density times pi d squared over 4 times V, so that's 0.766 times pi times D. D is 3 centimeters up here, so 0.03 squared over 4 times V. V is given, that is 5 meters per second up here. So times 5, let's type all this into the calculator. We get 2.7 times 10 to the minus 3 kilograms per second. Now that we have m dot, we can get an equation that is used because we know that the surface temperature is constant. We see that it's talking about evaporation. That's a good clue that surface temperature is constant. So we write this down. Because that's when this equation is applicable. And then we write down the following equation. We have ln of this dimensionless temperature term, surface temperature, exit temperature so the natural log of this is equal to negative HA m dot Cp. Again, this is only used when surface temperature is constant. And we know that because evaporation, if we look at our little temperature curve from thermo, this is during a phase change. That is temperature, and it's constant during a phase change. And during evaporation, the temperature is constant. So we have the exit temperature, we have the surface temperature, and we have the inlet temperature. Nice. So Ln, surface temperature, 110. Because these are differences, it doesn't matter if this is in Kelvin or Celsius. Minus exit temperature leaves at 150 C. We have Ts, which again is 110, and inlet temperature 250. Because both the top and the bottom are negative, this becomes a positive, so we don't have to worry about a negative inside the natural log. I'm going to replace this A with the surface area of a cylinder, because we do know it is a cylinder. It's a circular tube. That means a cylinder. So the surface area of a cylinder is pi dl. We are given H, that was 120. Pi times D, 0.03 L, divide by m dot, we just calculated that, 2.7 times 10 to the negative 3 times Cp, we're given that up here, 4187. This Cp value is actually not for air, that's for water. Cp value for air, this is in the wrong spot, this should be in the water. The Cp value for air is basically 1 times 10 to the 3. So 1.01 times 10 to the 3. So we type all of this in, and we get that L, just using algebra, we get that L is about 30.2 centimeters, 0.302 meters. So that's part A. Part B, we need the rate of evaporation. For this, we need to find first the Q dot. So we have m dot from the hot gas, the Cp, and then we have Ti minus Te. That is just the normal convection equation. So let's solve for Q dot. We have 2.7 times 10 to the negative 3 times Cp. Which Cp do we use? We're looking at the hot gas right now. And then we're going to use that to help figure out the evaporation of the water. So then you do the inlet temperature minus the outlet temperature. So we have inlet temperature 250 and leave at 150. So 250 minus 150. This gives us Q dot is equal to 272.7 watts. And now we need to figure out the rate of evaporation. So we know from energy balance that Q dot gas minus the Q dot of evaporation must be equal to 0. That's just energy balance. You can't lose more temperature than you have, or heat. So Q dot G is equal to Q dot evaporation. Great. So now we just have to figure out what formula to use for Q dot evaporation. Well, if you remember from thermo, we have m dot C, we have Cp times Ti minus Te. Cp delta T is actually H. Specifically delta HFG. And this m dot is for evaporation, because we're looking at evaporation. So m dot evap times HFG. So 272.7 is equal to m dot, that's what we're solving for. And then HFG. Hey, we're given that. We're given that for water, and that's exactly what we need. 2230 times 10 to the 3. 2230 times 10 to the 3. So we type this in our calculator. We get m dot evaporation is equal to 1.23 times 10 to the negative 4. And the units are kilograms per second, because we are looking at mass per time. So that is how we do this combustion question. It's a lot of thermo.